All right. I wanted to make a video about a situation where I have a conductor that has a cavity. There's a couple of things that I think can be confusing about that. And I also wanted to, look at a specific question about this scenario where I have the conductor, it has a cavity, which is basically a hole within the conductor where there is no conductor. And what happens if I put a charge in there? Now, your book goes through how the charges redistribute in that situation, but we're going to look at it in the context of a pretty specific question, which is, if I place a charge inside that cavity, will it affect the space outside the conductor? So I thought a good place to start would be to think about that conductor with a cavity, but in the scenario where there's nothing in it. So I made it sort of like a spherical shell because it's just easier to draw and easier to think about. And so here's our conductor, which has a cavity. So I tried to show with my beautiful shading that this area right here, like this represents the conductor and this is the cavity. So there's nothing in here. It's a hole, it's a void. Now, we're told that this conductor has a total charge of plus 3Q. Now, since we've learned about the characteristics of conductors, we know that any excess charge that resides on a conductor when it's in equilibrium will have to be on the surface. So our plus 3Q is all distributed on the surface of this conductor. And so now the reason it can't be anywhere else has to do with Gauss's law and the idea that right here, now it's important that I drew it where it's shaded. That is called inside the conductor. The cavity is not technically inside it because then you're not in the conductor because it's just a void. But inside the conductor, the electric field is 0. So that means anywhere closer to the middle than the very surface of it, if I took a Gaussian surface, like here, and I applied Gauss's law, I would have to find that there was no charge enclosed because of the requirement that there can't be any electric field in the conductor if it's in equilibrium. So for this, the idea is that we're doing this integral of E dot dA, which is equal to the Q enclosed over epsilon naught. We know that this is 0, which means that the Q enclosed also has to be 0. And that's why all the charge is on the surface. Now, and let's go one step further. Let's look at some sort of Gaussian surface outside the conductor. If I then do Gauss's law, and this is part of the reason that I made it a sphere, because then we're going to be able to use those approximations that, the electric field here and the area vector are parallel to each other, and so I can simplify this, and also the electric field is going to be constant on the surface, so this ends up to be just E times A is equal to the charge enclosed, which is plus 3Q over epsilon naught, and then the area is 4 pi r squared, and that's equal to 3Q over epsilon naught. And so the end result is that the electric field can be written as K times 3Q over r squared. And if you think about that expression for the electric field that we've arrived at, it looks the same as if there was a point charge with a total charge of plus 0.3Q located at the very, very center of the conductor. It does, the other thing is just to give a sense of what the electric field that conductor is creating. It looks like a point charge even though it only starts at the surface and then works its way out. Now what's going to happen to the same conductor with the same initial total charge if I place another charge at the center. So now I've taken my conducting shell and I've placed a charge of plus Q in the cavity. Now keep in mind that right here, if I look at the Gaussian surface somewhere in the conductor, this electric field has to be 0. And so when I'm doing Gauss's law, since that electric field has to be 0, it's also saying that the charge that I've enclosed by my pink Gaussian surface has to also be 0. And so how does that work? Well, what we learned is that what's happening now is that some negative charge will build up on that inner surface of the conducting shell. And that sometimes I think can be confusing because you might say, well, now it's inside, and you said it couldn't be inside, but it's still considered to be the surface of the conductor because of the way it's constructed, because this is the conductor itself, and so this is the inner surface. And the amount of charge that has to accumulate on that inner surface is minus Q, because then if you add the minus Q and the plus Q together, you get 0. And the idea is that what happens is when this plus Q, is created, is placed in there, it does create this electric field in this area. But then what happens is that the electrons of the conductor are kind of influenced to, move because of that electric field, and they will actually arrange themselves so that they are shielding this part of the conductor from the electric field that was set up within the cavity. So they're really shielding when they accumulate on that surface. And then you say, okay, well then, but my total charge of my conductor is plus 3Q, and right now, on the inner surface, I have minus Q. So that means that there has to be an excess of positive charge on the outside. And the excess of positive charge is plus 4Q, right? Because these two together have to add up to be 3Q, right? And finally, we have to ask ourselves, well, what does this look like outside of the conductor? So we take another Gaussian surface, because now we have this electric field looks like this, the area vector that looks like this. Now let's see what the end result is here today for the electric field that is created in this scenario. And so what we have is, this is just going to be E times A, which is equal to E times 4 pi r squared. Now how much charge do I have enclosed? We have to go one by one. I have plus 4Q and then minus 1Q. So that gave me plus 3. And then I have this other one of plus Q. So I had plus 3, and now I add 1, and I got plus 4Q. So I actually have enclosed a total charge now of plus 4Q. And so when I solve for the electric field of this scenario, it's K times 4Q over R squared. So that's kind of interesting if you think about it. What has happened is when we are outside of the conductor, in a sense, we can still see the effect of the charge that was in the cavity. But when you're inside the conductor, because of the behavior of the conducting material, the conductor itself never is subjected to an electric field within the conductor. And so we have a little bit of electric field in the cavity then no electric field in the conductor. And then once we get outside, the electric field has the strength that's equal to the charge of the conductor plus the charge inside. And the electric field that we see behaves as if all that charge was at the very center of the conductor, other than the fact that there's nothing really until we get to the surface, the outer surface. Interesting? Hopefully it makes sense. This looks really busy. I hope you could follow it.